Hello everyone, this is Dr. Thiessen, and I'm using this video to answer the famous probability question that is asked during the interview for a data science position. So here's the scenario. You're headed to Seattle and you want to know if you should bring an umbrella. So you message 3 of your friends who live there and ask each independently whether it is raining or not. So each friend tells you yes, it is raining, but there is a chance that they could be lying, and each of them have a 2/3 chance of telling the truth, as well as a 1/3 chance that they are lying. So let's represent the scenario. So we have here the probability of it raining. Then we have the probability of it not raining. So probability of raining is P, probability of not raining is Q, or 1 minus P. So now we have all 3 friends have said yes, but there is a probability that they could all be telling the truth or that they could all be lying, because remember, they all said the same thing. So we want to know now the probability of one friend telling the truth is 2/3, so the probability of all of them telling the truth is going to be 2 times 2/3 cubed, and the probability that they're all lying, it's 1/3 cubed. And so we have the probability of all the yeses, 8/27, being truthful, or all of the yeses being a lie, 1/27. So now we want to know what is the probability of all the yeses given that it's raining. So that's going to be P, which is the probability of rain, times the probability of all the yeses. The probability that they're all lying given that it is not raining will be Q times 1/27. And so what we want to know is, what is the probability of raining given the conditions of an all yes? We know what the general probability is. This is the prior probability of rain, it's P. But what we want to know now is the posterior probability. And if you remember from the Bayes equation, where it states that the probability of the posterior, A, that is given that it's the probability of it raining given that they are all yeses, is going to be the product of the likelihood, that is the probability of all yeses given that it's raining, times the probability of raining divided by the probability of all the yeses. So let's see what that looks like. So this is how that formula would be represented here in if we use our actual probabilities. So we have the probability of raining given that all yeses would be the probability of all the yeses given that it's raining times the probability of raining. So this scenario here, and if I can draw that, so this scenario is what we're interested in. So we know the conditional probability of that, which is P times 8/27, but what we want to find is the the posterior probability. So now we would have that probability now conditioned on the fact that we got all yeses. And so there are 2 scenarios where we could get all yeses, and so we have to factor that in. So we would then have this new equation. So the probability of it raining given all yeses is going to be the probability of a yes given that it's raining times the probability of it raining, and that's now conditioned on the probability of a yes. And so the probability of the yes is going to be the sum of these 2 probabilities, these 2 conditional probabilities, which is the probability of yes given that it's raining times the probability of it's raining, plus the probability of yes given that it's not raining times the probability of not raining. So this is our equation. This is the general equation. And if we know the actual probability of raining, we can actually solve for that. So that equation would simplify to P, which is the probability of raining, times the probability of all yeses, divided by the probability of all yeses given that it's not raining, and there should be probability of all yeses given that it is raining, plus the probability of all yeses given that it's not raining. And that further simplifies to this. We change the Q to 1 minus P because Q is the complement of P in this case, and it's further simplified to this. And that is the equation. So the probability of raining given that they were all yeses is going to be 8 times the probability of raining divided by 7 times the probability of rain plus 1. And if we knew the probability of raining, we could simply substitute that into the equation. So if we had a probability of raining of 0.25, then we could substitute that into our formula here, and we would get the probability of raining given that it's all yeses, and that amounts to this formula, and finally 0.72. So there is a 0.72 probability that it is raining if they all say yes.